Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. I am Dr. Alka Mehrotra and we will be discussing here the lesson 5, the gaseous and the liquid state. During this part of the program, we will discuss about the gaseous and liquid state. So the objective of this program are differentiate between three states of matter, solid, liquid and gas, describe the various types of intermolecular forces, interactions, London forces, dipole-dipole forces, dipole-induced dipole forces and hydrogen bonding. As we all know that matter exists in three different states, namely solid, liquid and gas. You are familiar with gases, liquid and solid in your daily life. You are aware that water can exist as a liquid, a solid that is ice, and as a gas that is vapor under different conditions of temperature and pressure. Now here we have already done in the junior classes that the differentiation between the solid and liquid gases are based on their intermolecular force of attraction. Now based on that we can differentiate like shape, volume, density, compressibility also. Now shape. Solid, you know, shapes are indefinite and it takes the shape of the vessel in which it is kept. Gaseous, indefinite shape. Volume, in solid, definite. Liquid, definite. And gaseous, indefinite, it fills the container completely. So the density, what about the density then? Solid has high density. Liquid, the density of the liquid is lesser than the solid but much higher than the gas. And in gas, the density is very low. Compressibility. Solids are incompressible. You cannot compress the solids. Liquids, largely we can compress, but in gaseous, the compressibility is higher. Now, these properties are dependent on the intermolecular forces. Now, the difference between these three states of matter is due to the difference in their intermolecular distances and intermolecular forces. In addition to these, temperature and pressure also play an important role in deciding the states of matter. The properties of gases state can be explained in terms of large separation of molecules and very weak intermolecular forces. Now we are going to discuss about the intermolecular interactions. Intermolecular forces can be described as forces of attraction and repulsion existing between the particles of atom and molecule in a compound. The force of attraction are called van der Waals force of attraction, which include dispersion forces or London forces, dipole-dipole forces and dipole-induced dipole forces. And the example of force of repulsion is electron of one molecule repel the electron of another molecule, and the nuclei of one molecule repel the nuclei of another molecule. Now let's discuss about dispersion force or London forces. We assume that electrons are evenly distributed around the nucleus. However, since electrons constantly move around the nucleus at a particular instant, the distribution of electrons may become uneven around the nucleus and result in generation of dipole with a slight negative charge on one side and an equal positive charge on the opposite side. So what happens? Thus, an ordinary non-polar species like an atom of a noble gas like argon or neon becomes polar species for an instant. And it was proposed by a German physicist, Fritz London. That is why it is named as London forces. Now I'll show you with the example. Let us consider two atoms, P and Q. Let the electronic charge distribution in atom P be unsymmetrical. Therefore, the charge cloud is denser at one side of the other. This leads to the generation of instantaneous dipole on atom P for a short period of time. This instantaneous dipole on an atom P alters the electron density of the atom Q placed close to it. This includes a dipole in the atom Q. The temporary dipole of atom P and Q attract each other. In the same way, temporary dipole are included in the molecules too. So, we can say this is a temporary attraction. Now, let's move on to dipole-dipole attraction. If molecules of substance are polar in nature, the positive end of one dipole attracts the negative end of the other. These interactions are quite strong as compared to the London forces and increase the melting and boiling point of polar compounds such as ethers, as compared to those of similar non-polar compounds such as hydrocarbons that have nearly the same molecular mass. Now, next is dipole-induced dipole forces. These interactions are between polar molecule and non-polar molecule. The polar molecule induce a dipole in the neighboring non-polar molecule and an electrostatic force of attraction starts operating between them. So, we can say about dipole-induced dipole forces that the magnitude of these forces depend on two factors. Number one, dipole moment of the polar molecule, and so the greater the dipole moment, stronger is the attractive force. And the number two, polarizability of non-polar molecule. So, more polarizable is the non-polar molecule, greater is the dipole moment of the induced dipole and stronger is the attractive force. Now, we move on to the hydrogen bonding. This kind of bond is found in molecules having high polar bonds, for instance, nitrogen-hydrogen, oxygen-hydrogen and hydrogen-fluorine. So, here the atoms which are more electronegative in nature will form hydrogen bond with hydrogen. So, hydrogen bonding is responsible for some unusual properties of water, like its existence in liquid state over a wide range of 100 degree, that is 273 Kelvin to 373 Kelvin, high heats of fusion and vaporization, and its solid form ice being lighter than liquid water. Now, let's revise what we have studied so far. We have done that matter exists in three states, namely solid, liquid and gas. And now I am sure you know about the properties of these. Then we have studied the three states of matter differ in the relative closeness of molecules constituting them. And we have studied about the intermolecular interactions present depending on the nature of the substance. So, what we have studied? We have studied that there are three states of matter: solid, liquid and gas. There is one more state of matter, that is plasma state, that we have not included in this topic. Now, as you know that solid, liquid and gases can be differentiated in various ways, and the major cause why they are differentiated, this is because of the intermolecular forces or intermolecular interactions. And we have studied like London forces, we have studied dipole-dipole forces, we have studied dipole-induced dipole forces and hydrogen bonding, and you have noticed that how they react and how they affect the substance or the nature of the substance. I am sure you have understood the topic. Thank you. Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. I am Dr. Alka Mehrotra and we will discuss lesson 5. In our previous program related to lesson 5 gaseous and liquid state, we discussed about part 1, types of intermolecular interaction forces. During this part of the program, we will discuss about the various gas laws. The objective of this program is list of characteristic property of gases, state the gas laws, Boyle's law, Charles' law, Gay-Lussac laws and Avogadro's law, and express these mathematically, and ideal gas equations. Now, let's discuss about the properties of gases. As you know, gases are highly compressible. I'll show you this with the help of a syringe. Now, if we put it up, you can see this is air. the syringe is filled with air. Now, I am going to put my finger down. So, I am closing this very tightly. Now, I am going to push it down and you can see this is going down slowly, slowly. So, what is happening over here? This is compressing the gas. It means the molecules which were very far apart are coming closer. So, we can say gases are compressible in nature. They exert pressure equally in all directions, and the best example for this is balloon. You must have noticed that in balloon, when you blow the balloon, the air goes equally inside the balloon. So, it means it exerts pressure equally in all the directions. Then, the density of them is much lower than solid and liquid. Now, what about density? What is density? Density is mass per unit volume. Now, we know that volume of gas we can say is higher. The mass will be very, very less between them, because if you see in lot of molecule, the volume is more, but the hardly few particles you will find. It means the mass is very less, so the density will also be very less. Then, the volume and shape of gases are not fixed. How can we explain this? For this also, we know that the molecules are very far apart. So, when they are very far apart, it's very difficult to bring very close and to give a proper shape. So, we can say the volume and shape of gases are not fixed. Then, they mix evenly and completely in all directions. There also we have lot of example where we can say gases are evenly mixed in many directions. There are 4 measurable quantities of gases. Only 4 quantities define the state of gas. Number 1, the quantity of gas, that is N, which we denote as N, which is a moles, number of moles, the temperature P, the pressure P, and the volume V. Now, let's discuss all the laws one by one. Boyle's law. Boyle's law, as you know, it is the effect of pressure on the volume of the gas. Now, Boyle's law was stated by Robert Boyle, that is why the name is Boyle's law. This law states that at constant temperature, the volume of a given amount of a gas is inversely proportional to its pressure. Now, I am going to show this to you. Boyle's law. Here, we are keeping 2 constant, that is temperature and number of moles constant. So, what Boyle has done, he kept temperature and number of moles constant, and then he checked the ratio or the relation between volume and pressure. And he found that volume is inversely proportional to pressure. So, we can write V is inversely proportional to P, that is V inversely proportional to P. Now, if you cross multiply, we will get PV is equal to, now we are removing the proportionality constant with the equal sign and we are putting a constant. So, we can say product of pressure and volume is constant. We can say that P1 V1 is equal to P2 V2. Now, I want to show you this, how he came to this conclusion. A very simple example, our day-to-day life. Again, we will take a syringe. Let's again assume that here the volume is there. Let's assume that there are 10 molecules are there of air. Now, what are we going to do? We are applying a pressure. Pressure is more and you can see it is going down. So, volume is becoming lesser. So, here this is what Boyle said, that when the pressure is more, volume will become lesser. This is what he explained here, that volume is inversely proportional to pressure. So, pressure is more, volume is less, volume is more, pressure is less. So, if we draw a graph by taking pressure and volume and by keeping temperature constant, this is known as isotherm. So, isotherm is a graph where the temperature is constant. Now, according to Boyle's law, we can say that if we have a perfect gas of a given mass at constant temperature, that is temperature which remains unchanged during the change of state of gas, and if the pressure of the gas increases, then the volume of the gas decreases, and if the pressure decreases, then the volume of the gas increases. So, the conclusion is that the pressure varies inversely to its volume at constant temperature for perfect gas. So, let's discuss about the graph. When the pressure of the gas P is plotted against volume of the gas V, the exponential curve is obtained. However, when the pressure P of the gas is plotted against 1 upon V, a straight line is obtained. If the product of P and V, that is PV, is plotted against pressure, a straight line parallel to x-axis, that is pressure is the x-axis, is obtained. Now we move on to the Charles' law. This is effect of temperature on the volume of gas. This states that at constant pressure, the volume of a given amount of gas is directly proportional to its absolute temperature, that is 273.15 degrees Celsius. This is the theoretically lowest possible temperature. In actual practice, we cannot reduce the temperature of the gas to 0 Kelvin. Now, I'll show you on board how he has arrived on this calculation. Charles' law. He kept the pressure and number of moles constant, and he found that volume is directly proportional to T. If we remove this proportionality constant, we get V is equal to KT, where K is a constant. Now, we can say that V1 upon T1 is equal to V2 upon T2. This is T2. Now here, if you have noticed, he said that we have to take the absolute temperature. Charles' law helps us to define absolute temperature also. Now, what is the meaning of absolute temperature? To understand better the absolute 0, now let's draw one graph kind of thing where we have 0 degrees Celsius, 1 degree Celsius, 2 degrees Celsius and in minus. So, what he said that when we add 273.15 to any given temperature, we get a Kelvin scale. Kelvin or the absolute temperature we get. Now, suppose if 0 degrees Celsius and you add 273.15, so what Kelvin you will get? You will get 273.15. Same way, if we add 1 to 273.15, we will get 274.15 and so on. Now, if we move backside, suppose the temperature is -1. So, how are we going to do it? -1 plus 273.15, we will get 272.15 and so on like that. So, to get absolute temperature or in Kelvin scale, we have to add the given temperature with 273.15 and we can get the Kelvin scale. Now, suppose if minus 273.15 temperature is there, so if you add 273 to it, what are we going to get? We get 0. So, 0 here I have mentioned. If we take this in degrees Celsius and you add 273.15, we get 0, which is the absolute 0. Now, absolute temperature is the temperature at which the volume of gas is 0. I hope this is clear to you. Now, we move to the Gaseous law. This is effect of temperature on pressure. This law states that pressure of a given amount of a gas at constant volume is directly proportional to its absolute temperature. It means P is directly proportional to T. Now, I'll explain this to you on board. As you know, the volume and number of moles are keeping constant, and the relation between pressure and temperature has been noticed that pressure is directly proportional to T. Now, if we remove this proportionality sign, we will have P is equal to K into T. K is a constant. Now, we can write that P1 upon T1 is equal to K. So, we can also write P1 upon T1 is equal to P2 upon T2, where P is the initial pressure, T1 is the initial temperature, and P2 is the final pressure and T2 is the final temperature. So, by keeping volume and number of moles constant, we have a relation between pressure and temperature. We can say pressure is directly proportional to temperature, or in other words, temperature is directly proportional to pressure. Now, let us remove this proportionality constant and we have P is equal to KT, where K is a constant. Now, we can also write P1 upon T1 is equal to K, or if we have initial pressure P1 and final pressure P2, initial temperature T1 and final temperature T2, we can have this relation that P1 upon T1 is equal to P2 upon T2. Make a graph of pressure and temperature. Let's take temperature on x-axis and pressure on y-axis. So, the relationship between the pressure and absolute temperature of a given mass of gas at constant volume can be seen over here, that you get a straight line. So, this shows that when pressure increases, temperature also increases. Now, few examples, very interesting example you must have noticed in your day-to-day life. Number one is bursting of tire in summer. You must have noticed that lot of tire get burst during the summer. So, what is happening over there? There we can explain this as a Gaseous law. Like in summers, you know, the temperature is very high and the volume is fixed or constant, but the pressure inside the tire gets more because the temperature is directly proportional to pressure. Now, because of the pressure more, and it can't expand because volume is fixed, so the tire get burst. Second example, which is very common, you must have noticed that people always say do not take aerosol and do not put fire in front of the aerosol. Now, I'll show you one example. You must have noticed aerosol. Now, this type of bottles you must have noticed, which is known as the aerosol. Aerosol can be where the gases can be compressed in a bottle. Now, whenever you spray it in front of a gas, or if you bring one matchstick near the nozzle of that, what happens over there? If you have noticed, it catches fire. Why? Because what is happening over here, when we are pressing it, pressing means volume is a constant, but the pressure which is there inside it get released, and because of the higher temperature, immediately it catches fire. And the third example, which is again a very interesting example, which is cooking food in pressure cooker. You must have noticed your mama makes food in a pressure cooker and it cooks very faster as compared to when you are making food or when your mama makes food in the open container. So, what is happening over there? You know, whenever we are putting anything like dal or rice in the pressure cooker and we are putting water in it and we just seal the cover of that. So, what is happening? Here, the volume is fixed. Now, when you are giving temperature to that, because of the seal lid, the pressure becomes very high and then you get a vessel kind of thing. So, as we are giving more temperature, so pressure becomes more. Because of that pressure, food cooks very fast as compared to the open container. Now, the next is Avogadro's law. Avogadro's law is that states equal volume of all gases at the same temperature and pressure contains equal number of molecules. So, mathematically we can say that volume is directly proportional to number of moles. I'll explain this to you on board, but before that I want to discuss one example. Now, that example is blowing of balloon. Now, when we are blowing a balloon, so what happens over there? The volume becomes more. Why? Because the number of moles we are putting inside it. So, when you are putting lesser amount of air, so the volume will be less. When you are giving more amount of moles in it, the volume will be more. So, we can say the volume is always directly proportional to number of moles. So, here in Avogadro's law, pressure and temperature are constant. When pressure and temperature are constant, so what two entities are left? Volume and number of moles. So, volume is directly proportional to number of moles, or if you remove the sign, we have volume is equal to Kn. Again, K is a constant. So, if you bring this n over here, we get V upon n is equal to K, or we can say V1 upon N1 is equal to V2 upon N2, where n is the number of moles, and this is the number of the molecules in 1 mole of gas is 6.022 into 10 power 23, and this is termed as Avogadro constant. So, here if you see 1 mole of any substance contain 6.022 into 10 power 23 number of particles or atoms or molecules, that depends what we have taken. Suppose if we talk about 1 mole of hydrogen, so 1 mole of hydrogen atom contains 6.022 into 10 power 23 number of atoms. But same way, if we talk about 1 molecule of hydrogen atom, so that contains 6.022 into 10 power 23 number of hydrogen molecules. So, at STP, what is STP? Standard temperature and pressure, where temperature we take at absolute, that is 273.15 Kelvin, pressure 1 atmosphere, or we can say 10 to the power 5 Pascal, and volume is 22.4 liter per mole. So, the number of moles will remain constant, that is 6.022 into 10 power 23. Boyle's law, Charles' law and Avogadro's law can be combined to give a single equation which represents the relation between the pressure, volume and Kelvin temperature of a given amount of a gas under different conditions. As we know, Boyle's law says that V is directly proportional to 1 upon P. Charles' law says V is directly proportional to T, and according to Avogadro's law, we have V is directly proportional to N. So, now let us combine all these laws. We get V is directly proportional to NT upon P, or we can say V is equal to nRT upon P. Now, R is a gas constant and it is same for all the gases. So, here we get an equation, that is ideal gas equation, that is PV is equal to nRT. Now, let us discuss what we have studied so far. So, here we have done that there exists definite relationship between the pressure, volume, temperature and number of moles of gas, and they are given by Boyle's law, Charles' law and Avogadro's law. The gases obeying gas law are known as ideal gases. Dalton's law gives the relationship between the partial pressure exerted by the two reacting gases in the total volume, and Gay-Lussac's law of combining volume and Avogadro's law led to the concept of molecule. Thank you. Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. I am Dr. Alka Mehrotra. We will discuss Lesson 5, the gaseous and liquid state. In a previous program related to Lesson 5, we discussed about types of intermolecular interaction of forces and various gas laws. Now, we will discuss kinetic molecular theory of gases and liquefaction of gases. The objective of the program is Dalton's law of partial pressure, kinetic molecular theory of gases, liquefaction of gases. Now, let us start with Dalton's law or partial pressure. It was stated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of partial pressure of individual gases. So, we can see here that if we have 3 different gases A, B and C, they have their own pressure. So, this is known as a partial pressure, and when we are combining them, we get a total pressure. Now, let us discuss this mathematically. As you have seen in the picture that partial pressures were there for different gases, and when we combine it, we get a total pressure. Now, by taking this information, we have total pressure, we can say that P1 plus P2 plus P3, that is a partial pressure. And we are keeping constant temperature and volume. We know that ideal gas equation is PV is equal to nRT. So now we can also write P is equal to nRT upon V. Okay, this is for the total one. Now let's take one by one for each. When P1 is there, we can say N1 RT upon V. Why are we not changing this? Because you know that this is a constant. So we are changing only the number of moles. As you have seen in the picture, the number of moles were different. So we can say for the first gas, P1 is equal to N1 RT upon V. For the second gas, P2 is equal to N2 RT upon V. And the third gas, P3 is equal to N3 RT upon V. These are the partial pressure. Now, by taking this equation, let's put the values of these P1, P2, P3 in the main equation. So we can say that P total is equal to N1 RT upon V, N2 RT upon V and N3 RT upon V. Now dividing, now we have this as a total pressure. Let's divide this P1 by total pressure. So what are we going to get? As you know that N1 is there, RT upon V, and for this also RT upon V will get cancelled because the values are same. So what we will get is N1 upon N1 plus N2 plus N3. How are we going to get this? This is the total pressure, because in the totality we get all the gases with different number of moles. Or when you add all, we can simply say N1 upon N. For pressure P2 also we can say N2 upon N. For P3 we can say N3 upon N. Now, we can also write P1 is equal to X1 P total. Now, what is X here? X is a mole fraction. Now, we can say P1 is equal to X1 P total, P2 is equal to X2 P total and P3 is equal to X3 P total. This was described by Dalton's. Now, next is kinetic molecular theory of gases. To explain the behavior of gases theoretically, Clausius, Maxwell, Boltzmann made the various assumptions. Now, for the first assumption was gases consist of large number of tiny particles called molecule. That we are familiar with that all gases are made up of molecules. Now, second is the gas molecules are so small and so far apart that the total volume of the molecule is negligible fraction of total volume occupied by gas. We can describe this by taking the example of compression. As we know, as this law states that the volume is very, very high. So, because of that, we can compress the gas. So, the compressibility, you can relate the compressibility with the second postulate of kinetic theory. Then, third is the molecules are in the state of constant, rapid and random motion, colliding with one another and with the wall of the container. When they are colliding with each other, that is why we say that gases do not have any shape, because continuously they are colliding with each other. They are continuously in the motion, so they do not have any particular shape. Then the fourth is there is no attractive or repulsive forces between the molecules of the gas. Now here, first think about liquid. Now, liquid, what happens? We can say that attractive forces are there between the liquid. I'll give you one very simple example. Whenever water spills on the table and we try to put a line along with that water, we find that the line can be made. Why? Because there is an attractive force between the molecule of the water. Can we do the same thing with the gas? No, we cannot do. Why? Because there is no attractive or repulsive forces between them, and that is why when we are filling air in the balloon get burst and the gas comes out. If there is any attraction, definitely the balloon will remain with the same shape. So, we can say that there is no attraction or repulsion between the gaseous molecule. Then fifth postulate is the collisions of the molecule among themselves and with the wall of containing vessel are perfectly elastic, so that there is no loss of energy during collision. Now, we can say this, that what is the meaning of first elastic collision? Elastic collision means on hitting, the exchange of energy will be there, but there is no gain or no loss of energy. The gain of energy will be equal to the loss of energy for the other molecule. So, this is known as the elastic, perfectly elastic vessel. Now, then the pressure exerted by a gas is due to the bombardment of the molecule on the wall of containing vessel. Here also we know that when you try to catch or try to put the gas in one of the container, they always try to apply the force on the wall of the container. Why? Because the molecules are very far apart, they just collide with each other and they try to apply the force. And the last one is the kinetic energy of a gas is directly proportional to the absolute temperature of the gas. Now here, if the temperature is more, the pressure will increase, and we can say the temperature is more, kinetic energy will be higher. Reason is, when we are giving more temperature to that, so the molecules will be agitated and they will start moving here and there. So, the kinetic energy will be more. If the kinetic energy is more, they will try to apply the pressure on the wall. So, we can say the temperature is also directly proportional to the pressure. But all the gases do not behave ideally. So, the gas law mentioned are strictly valid for ideal gas under all condition of temperature and pressure. Real gases show deviation from these law at temperature and high pressure. So, what are the deviation? Real gas is a gas which does not follow the ideal gas behavior under all condition of temperature and pressure is called the real gas. Here, we can explain this with the factor which is known as a compressibility factor. Deviation from the ideal behavior can be measured in terms of compressibility factor. So, when we say PV upon nRT, that is the ideal gas equation, it is equal to Z. So, for the ideal gas, Z should be equal to 1, there should be unity. So, we can get a straight graph, but real gas do not follow the ideal gas behavior and they do not show the value equal to 1. Now, thus, the straight line obtained for the ideal gas when V versus pressure graph is plotted, but for the real gases, different curves are obtained. Now, gases deviate from the ideal behavior due to the following faulty assumptions of kinetic theory. First is, as per kinetic theory, it was volume of molecule of gas is negligibly small in comparison to the space occupied by the gas. But contrary to assumption 1, the volume occupied by molecule of gas becomes significant at high pressure. As I have shown you with the syringe example, when we are applying pressure, the volume will become lesser. So, we can see that there is a significant volume of the gases are there. And the second faulty postulate was that there is no force of attraction between the molecule of gas. Now, this too does not hold good, as at high pressure molecular interactions start operating and gases can be liquefied. Now, so we can say that gases can be liquefied and the liquefaction of gases comes in the process. Now, how can we liquefy the gas? Gases can be liquefied easily by increasing pressure and decreasing the temperature. You must have heard about LPG, which is liquefied petroleum gas. So, what is the meaning of that? Meaning is the gas under high pressure and low temperature come in a cylinder and that is liquefied. So, the molecule of gas forcefully brought together to fit in the gas. Now, here we have few terms, that is the critical temperature, critical pressure and critical volume. Now, it may be defined as the temperature above which no gas can be liquefied is a critical temperature. You cannot liquefy any gas at any temperature. There should be a certain temperature at which the gases can be liquefied. Same goes for the pressure. You cannot apply any pressure and you just liquefy the gas into the liquid. No. At critical temperature, the pressure needed to liquefy a gas is known as critical pressure. Same goes with volume. The volume occupied by 1 mole of a gas at critical temperature and critical pressure is known as critical volume. Now, let's revise what we have done. Like most of the gases deviate from the ideal gas behavior. First, we have learnt about the ideal gas. We know the ideal gas equation. Then we have noticed that most of the gases do not follow the ideal gas behavior. So, the deviation of the gas from ideal gas behavior is due to the wrong assumption of kinetic molecular theory. Real gases can be liquefied under appropriate condition, that you know that critical temperature, volume and pressure should be there. In liquids, the molecular force are quite strong as compared to the gases, but weak enough to allow the molecules to move within a limited space and the intermolecular distance is short. Thank you. Hello learners, welcome to NIOS Studio. This program is based on senior secondary chemistry course. In the previous program, we have discussed about liquefaction of gases. I am Dr. Alka Mehrotra. We will continue the lesson 5, the gaseous and liquid state. During this part of program, we will be discussing the characteristic of liquid state, compressibility and diffusion. Now let's first discuss about the arrangement of molecules. You can see here like how the molecules are arranged in solid, liquid and gases. Now the molecules are very close to each other in solid. When it is like that, it means we can say the shape and the volume is fixed in solid. And they are all based on the intermolecular force of attraction. The intermolecular force of attraction is maximum in solid than in liquid, and in gases it is least. Then the space, solids, there is no intermolecular force of space between them, or we can say the negligible is there, while in liquid it is more than solid but lesser than gases. So, because of that we can come to the conclusion of the various property of solid, liquid and gases. Like solid have a definite shape, definite volume, while in liquid they have definite volume but not definite shape, but in gases they do not have any definite volume or the definite gases. Now characteristic of liquid state. Now we are going to study basically in this part liquid state. So let's discuss about the characteristic. As you have seen, molecules are held together by intermolecular force of attraction. Intermolecular forces in liquids are stronger than gases but lesser than solids. Very little space between them, hence molecule in liquids are closer than gases. Under normal conditions, liquids are more denser than gases and less denser than solid. They have fixed volume and take the shape of the container. Like suppose if you are putting water in the glass, you will say that the shape of water is like that, because the shape wherever we are taking, it will take the shape of the container, but the volume will always fix. Suppose if you are taking 5 ml in the beaker, or 5 ml in the test tube, or 5 ml in the cup, or 5 ml on the saucer, it will remain the same volume. Now molecules can slip so they can flow. That is very important point, because the fluidity is there in the liquid. They can always flow from up to down, higher to lower level. Now liquids cannot be compressed or very little compressible. So now what is the compressibility? Because all the properties you have already done in the junior classes, but compressibility now it's really very important. Compressibility of a substance is its ability to be squeezed when a force is applied on it. Liquids are largely incompressible. Like in previous videos, you have noticed when we were talking about gases are highly compressible. Now liquids are largely incompressible. It is because there is very little empty space between them and between the molecules. In contrast, the gases are highly compressible because of the large empty spaces between their molecules. Now, let us do one activity to make you more clear. When we discussed about gas, if you remember, I showed you again with this syringe only, and we have taken like this, and you have noticed that it was highly compressible. Now, what are we going to do now? We will check with the liquid. We have taken the water and we will fill the water in this. You can see the water is over here. Now, what are we going to do? This is stationary. Now, I am going to put my finger over here and I am going to press it down very forcefully, pushing the plunge inside, and if you also do, you will find, so you have to apply a lot of pressure and still you will find that it is not going down. So, why? Because they are incompressible. And why are they incompressible? Because the molecular gap, the gap between the molecules are not that much, very lesser. So, we can just apply a little bit and then we will find we are failed to compress it. So, this is how we can explain the compressibility in the liquids. Now, let us discuss about diffusion. Diffusion is the process of spreading of a substance from the region of higher concentration to the region of lower concentration. This was seen in gaseous state also, and in gases it is highly, the diffusion is more. And the best example was gas we have discussed about the agarbatti. If the agarbatti or incense stick is burnt in one corner, you can smell it in the other corner. Now, let us check about the liquid also. Now, diffusion occurs in liquid because the molecules of both the liquids are moving and help in the diffusion process. So, what can we say about the solid then? It means solid, the diffusion will be very negligible. Now, this also I will show with the help of the activity. So, now you can see we are going to put one drop of ink in the water. Okay, now see how it is going to diffuse. Very slowly it is getting diffused, and the reason for this is that the intermolecular gaps are there, space is there. So, the particles of the ink are getting diffused in between the gap between the water molecules, and slowly you will find that the whole water will become the ink color. Maybe you have taken blue color or black color, it will become like that. I will show you like this. First, I have taken the water, as you have already noticed, plain water. We put a drop of ink and slowly it was getting diffused. A drop gradually dissolves into the glass of water, and now you can see it is getting diffused and the water is becoming the color of the ink. So, we can show the diffusion by this activity. I hope this is very clear to you. So, now let us recap what we have done, that liquids have definite volume but no definite shape. These are the very, very important properties and are almost incompressible, that you have noticed, and they can diffuse, that also you have seen. Thank you. Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. In the previous video, we have discussed about gaseous state, in which I explained you about various intermolecular interactions, gas laws. In gas laws, we have discussed Boyle's law, Charles' law, Gay-Lussac law, Avogadro's law, kinetic molecular theory of gases, ideal gas equation, and the deviation from the ideal gas. I am Dr. Alka Mehrotra. We will continue lesson 5, the gaseous and liquid state. During this part of program, we will be discussing about liquefaction of the gases. So, I am going to explain the liquefaction of gas with the help of Andrews curves. Now, as you know, the gaseous, the intermolecular space is more and intermolecular force of attraction is lesser in gaseous state. So, how can we liquefy these gases? Then scientists found, and especially Andrews has worked on carbon dioxide. He noticed that gases can be liquefied by increasing pressure and decreasing temperature. the conditions of temperature and pressure under which gases liquefy were first investigated by Andrews in 1869. Andrews found that liquefaction could be brought about at all temperature below 33.1 degrees Celsius or 304.1 Kelvin. But above this temperature, no liquefaction occurred no matter how much pressure was increased. This temperature was therefore called the critical temperature for carbon dioxide. Now, Andrews has taken carbon dioxide and he tried to liquefy that gas, and he plotted a graph between pressure and volume. You can see in the graph that various temperature he has taken, and he plotted the graph between pressure and volume. Andrews' experiment investigated the behavior of carbon dioxide and analyzed the pressure P versus volume V at different temperature. What he observed, so let's see what was his observation with the help of the graph. Above the temperature of about 48 degrees Celsius, the carbon dioxide resembles that of ideal gas. It means carbon dioxide behaves as a gas if the temperature is above 48 degree, whether it is 50 degree or 51 degrees Celsius. Then he found that as temperature is lowered, the isotherm exhibit distortion which gradually increases. Now what is the isotherm? Isotherm is the graph where we have the temperature constant, now which is indication of deviation from the ideal gas character. Then he noticed that around 31.4 degrees Celsius, it means when the temperature is decreasing, so the kink is observed which suggests that gas can be liquefied under compression. It means he noticed that carbon dioxide can be compressed only when the temperature is around 31.4 degrees Celsius. Above that, carbon dioxide behave as a gas only. Now, as the temperature is lowered further, the kink spreads into the horizontal line, and that is compression produces liquefaction. It means carbon dioxide can be liquefied at 31.4 degrees Celsius. Now, let's check again this thing and try to understand this. You can see the temperature is 48 degrees Celsius where it is behaving, carbon dioxide behaving as an ideal gas. So, the graph it's showing like a gas. So, 48 degrees Celsius carbon dioxide is like a gas. Now, slowly the temperature is decreased. Again, when the temperature reached around 31.1 degrees Celsius, you can see a little variation, a little kink is seen over there. Now, when the temperature, you can see when the plot is, when the graph was plotted, A to B, it means what exactly is there A to B? It is behaving as a gas. Now, at B, what happens over there? The liquefaction of the gas just starts at B. So, the gas condenses at constant pressure from B to C. Now, so that liquid and vapor phase coexist. That is why you can see in the graph that the straight line can be seen from B to C. It means vapor and liquid phases are coexist over there. Okay, now at C, the gas is completely in the liquid phase. You can see again, now again there is going to be change from C to D. C to D, you will find that it is behaving as a liquid. So, from C to D, the slope is very steep. Since a liquid is almost incompressible, we cannot compress the liquid. Now, how? Why we cannot compress the liquid? Because as you know, from gas to liquid, the molecules are getting little closer to each other. Now, when they are little closer to each other, it means it is very difficult for them to compress. So, that is why he noticed that this was his observation. So, then he said that it is a critical temperature. So, critical temperature can be defined as the temperature above which a gas cannot be liquefied. However, high pressure may be applied on the gas. You have seen that above 31.4 degrees Celsius, it was in the gaseous state. So, we can say that 31.4 degrees Celsius was a critical temperature for carbon dioxide. Then critical pressure. It is the pressure required to liquefy the gas at critical temperature. It means how much you apply the pressure, gas will not change into the liquid phase. Then critical volume. the volume occupied by 1 mole of gas at critical temperature and critical pressure, these together are called critical constants. So, critical constants are very important to liquefy the gases because above that you cannot liquefy the gas. So, critical constants are really very important. So, these are few critical temperature and critical pressure for different gases. So, now let us sum up. A gas can be liquefied. You know what is a liquefaction means? The molecules of gases we know are very far apart. Now, if you have to liquefy, definitely we have to come closer. We have to bring the molecule closer to each other. So, gas can be liquefied only if it is cooled up to or below its characteristic critical temperature. There exists a continuity of liquid and gaseous state. That is, they are two distinct stages of continuous physical phenomena. So, we can say it is the same material, but the states are different. Thank you. Hello learners, welcome to NIOS Studio. This program is based on Senior Secondary Chemistry course. In the previous section, you have learned that liquids have definite volume but no definite shape and are almost incompressible and can diffuse. I am Dr. Alka Mehrotra. We will continue lesson 5, the gaseous and the liquid state. During this part of the program, we will discuss about evaporation, vapor pressure, surface tension and viscosity. Evaporation. Evaporation is the process by which liquid changes into vapor. It occurs at all temperature from freezing point to boiling point of the liquid, and evaporation is a process which we see in our day-to-day life also. Suppose if you are putting water anywhere, next day we don't find water, it means the water drop that has been evaporated. Now, there are few factors that affecting evaporation. Rate of evaporation of liquid depends on temperature, surface area of the liquid exposed to the atmosphere, wind speed and humidity. Now, how? Surface area, more the surface area, faster will be the evaporation. For example, spreading of clothes for faster drying. This is very common example which we see in our home. We never put cloth just a crumble form when we have to dry, we just spread it. Now, why? Because when we are spreading, surface area is more and the cloth gets drier little faster than heat. If we supply heat to the liquid, evaporation is faster. The wet clothes dry faster in sun. Now, in rainy days, you have noticed it takes lot of time. Why? Because humidity is there, the moisture content is there. The increase in temperature increases the kinetic energy of the molecule of the liquid and the liquid evaporates at faster rate. And all this depend on intermolecular force. Stronger the force, fewer molecules escape. In alcohol, let us compare alcohol and water. Alcohol and water, if you just put one drop, so we will find alcohol evaporates faster. So, what happens? In alcohols, the attractive forces are weaker than those in water. Hence, alcohol evaporates faster than water. You know that the liquid placed in open vessel evaporate faster if we compare these two. If, however, the liquid is allowed to evaporate in closed vessel, evaporation occurs, but after some time, the level of liquid does not change any further and becomes constant. In the beginning, the rate of evaporation is greater than the rate of condensation. Now, here you can see. First, I have taken the open vessel, evaporation is seen, and the second you see the vaporization is more than the condensation. Then slowly vaporization is equivalent to condensation. So, this is how the vapors which apply pressure on that, this is the vapor pressure. But as more and more molecule accumulate in the space above the liquid, rate of condensation gradually increases. After some time, rate of evaporation becomes equal to the rate of condensation, and equilibrium state is reached. These molecules exert certain pressure over the surface of the liquid. The pressure applied by the vapor on the liquid surface is known as the vapor pressure. So, the pressure exerted by vapors above the liquid surface when these are in equilibrium with the liquid at a given temperature is known as vapor pressure of the liquid. So, this is one of the properties. Now, what factors affecting the vapor pressure? The vapor pressure of the liquid depends on the nature of the liquid. It depends on the temperature. Vapor pressure increases with increasing the temperature. So, when we are increasing the temperature, what happens? Kinetic energy is more. If kinetic energy is more, it means the velocity of the molecules are faster. They will just escape out. Okay, so the vapor pressure is directly proportional to the temperature. Then here comes one term, that boiling point. The temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure is called the boiling point. You have seen that what is the vapor pressure? Vapor pressure is nothing, just the pressure applied on the liquid surface is the vapor pressure. Now, when this vapor pressure is become equivalent to the atmospheric pressure, at that particular temperature, anything starts boiling, like in water. So, at 1 atmospheric pressure, boiling point is known as its normal boiling point. Now, there is a vast difference between evaporation and boiling. As I said before, evaporation is taking place all the time. This time also somewhere evaporation is taking place. Because now also, like suppose if you see the ocean, river and all, with the help of the sun rays, the evaporation is taking place. But boiling cannot take place at all temperature. It takes place at a definite temperature. And what was that temperature? The temperature at which the vapor pressure is equal to the atmospheric pressure. At that particular temperature, boiling takes place. Then evaporation is a slow process because it is continuously going on. Boiling is a fast process. You have noticed when you have put water in a pan and the gas, it's a fast, at particular temperature it starts boiling. Now, evaporation occurs only at the surface of the liquid. So, we can say it's a surface phenomena. Only the molecules which are at the surface, they will get evaporated faster because they are directly in direct contact with the atmosphere. And boiling occur throughout the liquid. So, we can say boiling is a bulk phenomena. When water is boiling, it does not mean that water is boiling only at the surface. Water is boiling throughout. So, it is a bulk phenomena. So, there is a basic difference between the evaporation and boiling. Now, when a small quantity of water is poured on a clean glass plate, now I am going to tell you about the surface tension basically. When we take a small quantity of water and we pour on a clean glass plate, it spreads in all direction in the form of a thin film. You all have noticed. Now, but when we take a small quantity of mercury and is poured on the glass plate, it takes the form of spherical drop. You may say that you have not seen the mercury, but yes, you have noticed, you must have noticed any thermometer when it breaks, we find that mercury comes out from that. And if you try to pick those mercury droplets, it's very difficult to take it out. Why? And it is always in a spherical drop form. So, we can say it means there is some difference between the arrangement of the water and the mercury. Similarly, small quantity of water is poured on a greasy plate. It also takes the form of small globule like mercury. Please notice this thing. If you take the normal plate and put little oil on it and put water and both the plates, you will find the difference between the water droplets. Now, this shows that the behavior of liquid is controlled not only by the gravitational force, we can say the weight, but some other forces also act on it, which depends on the nature of the surface in contact. If the weight of the liquid is negligible, then as the shape is preferably spherical, like raindrops, soap bubbles, you find that they are the spherical shape because the area is lesser. Raindrops, basically we say it's a distorted spherical shape. It's not exactly spherical, but it is a distorted form. Okay, I'll explain this surface tension by this figure. You can see, we will compare the water molecules at the surface and the water molecule which is there in between the water. Molecule B lying inside the liquid is surrounded by other molecules, and so is attracted equally in all directions. Hence, the net force of attraction acting on the molecule is 0. A molecule A, which is lying on the surface, is attracted more by the molecule lying in the bulk of the molecule, it means from the downside, than by the molecules lying above it in the vapor phase. Therefore, the molecule A experiences a net inward attraction or inward pull. As a result, surface behaves as it were under tension, because the surface is getting pulled by the water surface, because it is not the net force is not 0 here. We can say it means the tension is developed over there. So here we can say as it is developed on the surface of the water, so the name is given to the surface tension. So what exactly is surface tension? It refers to the amount of force performing per unit length and is perpendicular to the line on the surface of the liquid. So surface tension formula is, we can say F upon L, or force per unit length, and it is denoted by the Greek letter gamma. Unit is Newton per meter. As you know, force unit is Newton and the L, that is length unit, is meter. So we can say the unit is Newton per meter. Now, surface tension decreases on rising the temperature. When we are increasing the temperature, so what happens? Kinetic energy of the molecule is more, and that decreases the intermolecular force of attraction. So, consequently, the surface tension decreases. Now, surface tension we can see in our day-to-day life also. The first few examples are there. First is spherical shape of liquid drop, that is what I told you just now. It takes the shape of the sphere because the area of that is lesser. So, wetting and non-wetting property means like water wets the things like cloth and all. Now, non-wetting property like mercury. If you put mercury like in thermometer, we jerk the thermometer before taking the temperature of our body, and it does not stick on the surface of the glass. So, we can say that this is a non-wetting property. I will explain this further later on. Before that, I will come to the capillary action, and I want to show you one activity of that. Capillary action. Before I show you this activity, I just want to tell you one example of that, which is of day-to-day life, that you have noticed that the plants carry water and minerals. And if you have noticed in your previous classes, like if you take a white color flower and you put in the ink, that is blue or red color, the water rises over there, and after some time the white color flower, you will find that it becomes the ink color. So now I will show you the activity. This is a paper. Now, paper I am going to put in the ink. I have taken the ink. Reason is the ink water, because you can see it very clearly. I am not going to dip completely. I will just put the water. This you can see water I have taken. Rather, let me little bit fold it so it will be more clear to you. Just the end of this will be touching over there. Can you see it? See, now what is happening? You will find that, or I'll do one thing for your better understanding. See, I'll put it over there, and after some time we'll see how much it has taken the water, because I have made paper touch only to the surface of the water, not more than that. And let's see how much water is raised on the paper. Now let's check. See. So have you noticed, maybe just not 1 minute also, 30 seconds, I put this, only this much surface on the water surface, and it has taken water till here, you can see. So this is the capillary action. So how this goes? Water is taken by the other molecule, other molecule, other molecule, so it rises up. So this is how it goes up. Is it clear? So now you can see the water has raised till here. So this is the capillary action. So from the, the molecules of water are getting raised up and up. So this is again a property, or we can say this is again a surface tension. Okay, the other effect of surface tension is curved meniscus. What is a meniscus basically? You can see here I have taken water and mercury. In the water, if you put both in the test tube, we can see in the first test tube, this is the concave meniscus is formed when the particle of liquid are more strongly attracted to the container, that is the adhesion, and than the cohesion, causing to the liquid to climb the walls of the container. Now, this is very new to you. What is cohesion and what is adhesion? Now, what is the meaning of that? Cohesion means when the molecules are attracted towards each other, and the adhesion means when the attraction between the water molecule and with the surface on which it is kept. Like we have taken water and we have taken mercury in the test tube, right? Now, water, the cohesion molecule will be lesser than the adhesion, that is why the test tube becomes wet. So, when you are putting both, you just remove the water from the test tube, you will find the test tube becomes wet. While when you are taking the mercury in the test tube and you just remove the mercury, you will find the test tube becomes totally dry. So, reason is that the adhesion means the attraction of the molecules of the liquid and the surface on which it is kept, the attraction is there. So, that we will find in the water case, but in the liquid case we can say the cohesion is more. It means the molecule of the mercury are more attracted towards each other rather than the molecule of the mercury and the attraction with the surface. So, conversely, a convex meniscus occur when the particles in the liquid have stronger attraction to each other than to the material of the container. So, we can say in water we have the concave meniscus. You can see the meniscus shape, while in mercury case it is always a convex because cohesion is more than the adhesion. Now, let us start viscosity. Some liquids like glycerol or honey flow slowly while others like water and alcohol flow rapidly. This difference is due to the internal resistance to flow, which is called viscosity. Viscosity arises due to the strong intermolecular forces between the molecules that holds them together and resists the passing of layers over each other. The layers of molecules of flowing liquid that are in contact with the surface are stationary. Increase in the distance between the two layers increases the velocity of the upper layer. Flow of liquid with regular gradation of velocity while passing over other layer is termed as laminar flow. Now, I want to show you before I discuss anything first example of both. I will show you this with the activity. Now, we will compare the more viscous and there is no viscosity in the liquid. Now, let us compare the flow. I am going to pour this water into the glass and you can notice the flow. It is very easily, very rapidly it occurs. If we pour gum on the plate, you find it takes time also and it is quite viscous, very, very viscous liquid is this. Now, when we can say that it goes in the layers of the molecule flowing liquid that are in contact with the surface, that is the stationary. I want to explain this understand in this way. Suppose this is one plate, another is this one. How to understand the viscosity better in this way? These two are suppose stationary phases. When these two stationary phases are there and suppose in between the water molecule is there, we can flow the water very, very easily, because intermolecular force of attraction is lesser in this as compared to the gum or the honey. Let us take honey now. Suppose honey is there in between. This is known as the stationary phase. When we are pouring honey like this, so the honey layers, you can see because the distance between the layers over there, the layer of the honey which is directly in contact with my hand or the surface will go little slowly. The above which are there will move little faster. The above will move little more faster. So we can say this flow is a unique kind of flow is there. This is known as the laminar flow, and we can say the gradation is formed over there. So that is why what happens, you will see that when it is flowing, the above layer comes faster than this layer, because this is in contact with the surface of the container in which it is kept. So the intermolecular forces, that cohesive forces, and each layer experience a force of friction from the adjacent layer, which I just told you. So this force of friction, that is F, is present between the two layers of them. So now I am going to tell you all this I'll explain this on the board to you. As I showed you on the experiment, the layers, how it works basically. So I drew over here, you can see, suppose this is the surface on which the liquid is kept, that is the honey is kept, and it is the laminar flow. This is what I explained to you earlier. So due to the intermolecular forces, cohesive force, each layer experiences a force of friction from its adjacent layers. This force of friction, F, between two layers depends on the area of contact between them, A, distance between the layers, that is this and this, that is dx, and difference in velocity between the layers, this is du, and the difference how it comes, that I explained to you. The layer which are away from the surface will move faster than the layers which are near or the closer to the surface. Now, taking these quantities, all are they related? We can say that this is a force of friction. We get a formula, F, that is force of friction, is equal to eta A du upon dx. So here eta is a Greek letter. It is called the coefficient of viscosity, and du upon dx is the velocity gradient between the layers. Now, how we can reduce the viscosity unit? As we know that if we take this one in the CGS unit of viscosity is dyne per centimeter square, or if you take MKS, we have Newton per meter square, or we can say it's a Pascal second. So the two units and otherwise the viscosity unit is also known as a poise. So we can say 1 PAS is equal to 10 P or 10 poise. Now viscosity depends on temperature and pressure also. Viscosity decreases with increase in temperature. With increase in temperature, as you know, kinetic energy of the molecule of liquid increases, which can overcome the intermolecular forces, hence the liquid starts flowing faster. So if you heat it, the molecule will become a little lesser viscous. Then viscosity increases with increase in pressure. On applying pressure, the molecules tend to become more closer to each other, hence liquid starts flowing slowly. Now let's sum up what we have studied. Boiling point, first we have done the difference between the evaporation and boiling point. Boiling point is what exactly? It's a temperature at which the vapor pressure of the liquid becomes equal to the external pressure. Then we discussed about surface tension. It is a force acting on an imaginary line of unit length drawn on the surface of the liquid and acting perpendicular to it towards the liquid state. And due to the surface tension, liquids tend to have minimum surface area and show phenomena of capillary rise or fall and curved meniscus. This I showed you with the help of the experiments. Viscosity is and then we discussed about viscosity. Viscosity is the internal force of friction to the flow of liquid. Thank you.